When computers first appeared in the 1950s, they were the size of entire rooms and could not perform the tasks even a pocket calculator today can. Now personal computers are a part of everyday life and are getting faster all the time. The speed of computers has doubled about every 2 years, but this technology is now reaching a limit. Information is transferred by the flow of electricity. This makes up the zeros and ones of computer memory. Devices are being made smaller to carry information faster, but at small enough sizes, the bizarre world of quantum mechanics begins to take over. We want to get our information from point A to point B, but it is now possible for our information to disappear and reappear somewhere we don't want it to. So scientists are working on new ways to store and transfer information. One way is to use the electrons themselves. Each electron has a tiny magnetic field, much like that of a bar magnet. Instead of using the flow of electrons to form the zeros and ones of computer memory, we could use the north and south poles of these magnets to do the job. There's a bonus to using this method too. Since the magnetic field of the electron is always on, no power would be used to leave a computer sitting idle. This would dramatically cut down on power consumption. There's a problem, however. Magnetic fields require a lot of power, and they tend to form ring shapes. This is a shape that does not like to be confined to small spaces. When a magnetic field is used to change a byte between 0 and 1, it could also affect nearby bytes, causing information to be lost. So scientists are using another approach. In 1894, Pierre Curie suggested that it was possible to use electricity to control magnetism in a material, and this was later found to happen in chromium oxide. This gives another way to control the magnetism without using large, power-consuming magnetic fields. But in the 1970s, scientists found that this effect was much stronger if one combined a magnetic and an electric material. The phenomenon, called magnetoelectricity, takes place at the boundary of the two materials, where they are placed in contact. By controlling the electric material, one can control the magnetic material as well. But even today, the way the process works remains a mystery, so careful study of the physics of this boundary is needed. But how can we learn about what happens at this boundary? There's no way to see with a microscope what the atoms deep inside the material are doing, so how do we have any hope of understanding this? Fortunately, there are other ways. One method is to use a laser, which is capable of going through the material and accessing what our eyes cannot. When laser light passes through the material and reflects back, it is altered in subtle ways. One way is that where there was originally red light, there is now also blue, and this part of the signal comes directly from the boundary. By carefully examining the signal, we can get information about the crystal structure and electric and magnetic forces at the boundary. This gives us access to the materials that would be otherwise impossible, and enables us to understand the details of this process and how to maximize this control of magnetism. By understanding the physics of this boundary, faster, more energy-efficient computers can become a reality.